to say something for the people who are online. So if you're online and you have a question to ask, for now, we'll try to have you just just unmute yourself and ask the question on Zoom. If you have a question that you want to address live, that's how we'll do it if you're online. And if it gets too hectic, then we can switch strategies. Okay, great. So thanks.
Thanks. And the other thing, even online, if you don't hear me well, let me know. I'll try to talk louder. So, okay, in this lecture, which we'll see how to draw those pictures that we were drawing in the last lecture. So I'm going to talk about belief propagation. I should warn you that I'm very far from being an expert on this topic. So maybe a good thing, maybe a bad thing. We'll see. All right. So what is the goal of belief propagation? Well, you have this distribution, the posterior distribution. Just to remind you, it's e to the minus beta g of x, where g of x is this quadratic. And our goal is to, compute the, let's say, the marginals of each variable. For each vertex I, you want to know what's the probability that xi is 1. So I think as I've described it, the problem is a little bit annoyingly trivial because of symmetry. The expected marginal of every variable is 0, because if there's some probability of being +1, there's an equal probability of being -1, just because of the symmetry of the model. But that's not really interesting. So let's ignore that issue throughout the talk. Let's assume that you have somehow conditioned on one of the signs or something. So, but really you have some Boltzmann distribution, which looks like e to the minus beta g of x. And you want to estimate the marginals. Okay. Okay. So, right. So, okay. So how do we estimate the marginals? Well, let me start writing something. So, okay. So let's. So just to write down what the marginal is. So the probability that let's say vertex u is equal to some value sigma u. Okay, this is of course equal to sum over all x with xu equal to sigma u of e to the minus beta g of x divided by z of g. Okay, sigma u is, let's say, +1. So the probability that it's +1 is exactly this. Okay, so the numerator is something where you are summing up these e to the beta g of x only on assignments x, where the vertex u is assigned sigma u. Okay, just think of sigma u is +1. So the numerator, we'll call it something else. Let's call it z of g conditioned on xu equal to 1. Okay, so that's what the numerator looks like. Okay, so that's good. All right, so now, so here's what we'll try. We'll try to do the following. You have a graph, your vertex u. I'm going to draw the vertex u outside. And then the vertex u has a neighborhood. It has a neighborhood. And let me call n of u are the neighbors of vertex u. Okay. And, we do the natural conditioning idea here. So we say, okay, well, this is, of course, equal to sum over z of g.
Xu equals sigma u, right?
Oh, sorry. Yeah, xu equals sigma u. Yeah, thanks. Sorry. Thanks. Okay, so we'll say xu equal to sigma u, and x rest of the neighborhood of u is also equal to some condition of the neighborhood. Okay, so divided by z of g. Okay, so if I condition on the neighborhood, then I can write the terms in this sum. Well, sorry, it's a sum over all x such that the entire neighborhood of u is assigned sigma n of u. Okay, and xu is assigned sigma u. Okay, so now if I condition on the entire neighborhood, then I can take out the contribution of the neighborhood to the Hamiltonian, to the g of x. So I'm going to write.
That sounds like it's not over x, it's over all the sigma and u, right? It's over all.
Oh yes,
like,
thanks.
To the d or 2 to the side of the neighborhood.
Thanks. Yeah, thanks. This sums over all the sigma of. Okay. Thanks. All right. So then, okay, if I, because of this conditioning of in the entire neighborhood, I can write this as sum over all the assignments to the neighbors. Okay, all the 2 to the d assignments to the neighbors. And then I can take out the contribution to the neighbors, because it's fixed now, because all of the terms in the neighborhood are fixed. So for every every term in the neighborhood is fixed, because all the edges, both endpoints are fixed. And then you have the rest of the graph. So let me call that g minus u, right? So let me call that g minus u of x. Okay, so essentially the Hamiltonian, or the g of x, splits into the edges that you see here and the rest of the graph, and you can write it this way. Sorry.
The neighborhood. You have to remove the neighborhood, not just two.
Oh, well, you take out all the edges going in. Yeah.
So you just remove u and you keep the neighbors, just remove
Oh,
the
okay,
edges.
okay.
Yeah, you remove the edges going from you, and so you're left with the graph of the remaining. Okay, and well, what is this? I'm going to start using proportionality, because I don't want to keep track of normalization factors.
So here, so here you are summing. You have like another sum over x. It's sum over
Yes,
sigma and
sum over x. Also, yes, sum over x and sum over sigma. Yeah, and so then this is proportional to, well, I'm just going to so sum over sigma and x. Okay, so what I'll have is I'll go back to sum over sigma so that we can see what's going on. Sum over v in the neighborhood of u, sigma v times z of g minus u conditioned on the neighborhood. It's yeah. It's okay, and well, all I want to say is that this quantity is like the probability, is proportional to the probability in g minus u of the neighborhood being assigned sigma. Okay. So it's just a Markov property of this graphical model that once I condition on the neighborhood, I know exactly what's the probability of the entire space, knowing the probability on the left and the probability on the right. And so that's there are probably much more cleaner ways to do this, but I probably butchered this. But what I wanted to get to was just this expression. Okay, this expression is something that's true in every graph. Okay, it's just this idea that the probability distribution on G is the probability distribution on G minus U. You take the probability distribution on G minus U and you reweigh the distribution by the Hamiltonian of the neighborhood, just the e to the power minus just the edges here. Okay, it's a very simple equality. Okay.
It's like the Markov property of Markov.
Yeah, it is exactly that. It's just Markov property. Yeah, I mean, I didn't have, yeah. Okay, so this is just true in every graph. Okay, just so far we're in good shape. Okay, so I'm going to copy that statement here. Okay. Sorry. Okay, I don't know why the animation here is messed up. I'm sorry about that. Ignore this thing for now. Pretend you don't see it for now. Okay. So, so what is okay? What do we do now? Let's just imagine G is a tree. A graph is a tree, and see what happens. Okay. So, okay. Firstly, this equation is very nice because it's expressing what we want to compute on the original graph as in terms of probabilities that you want to compute in G minus U. So there's some sort of recursion going on. But the problem with this recursion is that the left-hand side is a degree 1 marginal. It's about what happens in condition 1 vertex. And you're ending up trying to compute that in terms of the marginal of the entire neighborhood. I need to fix all these variables. So let's see if there's a way around it. Well, there is a way around it if your graph is a tree. Well, if your graph is a tree, then when you look at this variable u, and then you have subtrees here. Once I delete this vertex, I have trees that are disconnected. What that means is the neighborhood, all the vertices in the neighborhood become independent once you delete that vertex. Okay. And so that's a huge simplification now, because the joint distribution of the entire neighborhood is a product distribution. Now we can figure out the joint distribution of the entire neighborhood in terms of just the individual marginals of each of the nodes here in the neighborhood. Okay. So this quantity in a tree becomes a product over all the neighbors. That particular neighbor is assigned the value. Right, so in a tree, they have this huge simplification. And so now if you once on a tree, you really have a nice recursion, because the left-hand side is a degree 1 marginal. Degree 1 marginal as it's a margin of a single vertex. And the right-hand side now is also a degree 1 margin. Okay, so we can hope to use this relation on a tree, and as you can remove vertices and it's like dynamic programming. And in fact, all you need is some definition here. So let's define this Mij. This Mi to j is the marginal distribution of vertex I if j were absent. So it's basically, if I delete this, once I delete this vertex u, I want to know what is the marginal distribution of each of these roots of the subtrees, or each of these vertices v. Okay, and so what you really want to know is the marginal distribution of this vertex v in the situation where the vertex u did not exist. Okay, well, meaning after you deleted vertex u. Okay, and if you had defined this Mij, then you can you can actually write down the marginal of u in terms of the marginal of the neighborhood of u. Right? You can write a relation which looks like the marginal of vertex u is some function psi of the marginals of all the incoming values v to u.
You do have this notion that you just have the proportionality rather than equality. Is that an issue?
Well, no, not really, because so in some sense the proportionality. What does proportionality mean here? Well, this side, the left-hand side, is a function of sigma u, right? It's some function h of sigma u. Okay, and what we know is that we can calculate h of +1 and h of -1. Okay,
So then, you know, it sums up to 1, so you're good.
You normalize it.
Yes.
You can, right? This is a good question. Yeah. So you can just normalize it. You compute h of +1, h of -1, then you normalize it. Then you get this. Okay. So that's it. So basically, in a tree, we have this nice recursion, and you have a dynamic programming type algorithm, and it's also has this nice form where for every vertex, in some sense, you have on the edges, you have these marginals which every other neighbor sends it. Okay, so m v to u, m v prime to u. So you have marginals coming in at every vertex. And what does this vertex do? It applies this function on it, and that becomes its marginal. So if in a tree, if you think of a tree as having a root and so on, the outgoing message from this vertex u to its parent w is a function of the incoming messages. So you say mu to w is actually this function of these incoming messages. Okay. Yeah. So that's on a tree, everything works fine. So what is the algorithm on a tree? Well, let's say you don't have to do it, but you could do it this way. You root it, and then you start computing the marginals bottom up, and you get the marginals. Okay, so that you can do that. Okay, so what is the cavity method? Well, the cavity method is, now we have this definition of messages, and we have a way to calculate things on a tree. And in many situations, locally, things do have this cavity property or the cavity hypothesis that they'll behave like the tree, meaning the values of the neighbors of u are independent once you condition on u. Right. So this is a hypothesis, right? So we are making this assumption, and we'll proceed after we make this assumption. So it's an assumption that we have to making. Okay. Okay. So why is such a thing true? Well, the reason you'd hope such a thing is true, let's say in all our problems, is that if I look at a graph, okay, look at the vertex u, okay, look at all its neighbors. Okay. As we saw in the beginning of the last lecture, the neighborhood of every vertex looks like a tree, meaning all the cycles are long, right? All the cycles are long. So in particular, if I look at two vertices v and w here, okay, if you want to go from v to w, you have to take probably a long path, probably like a log n length path to go to from v to w, because typically cycle sizes are like order log n in these graphs. So, so in some sense, if you took away the vertex u, you think that the neighbors are far away from each other, so they become independent. But there are many. That's probably a reason, reasoning to say, okay, maybe this is true, but let's just proceed right for now, assuming this is true. Okay, so assuming this is true, what can we do now? Well, we can try to use the same update rule in a general graph. So in a general graph, you have all the vertices here. On every edge, you have, on every edge UV, you have two directions. You have two variables associated with it. One is the message from U to V, and the other is a message from V to U. All of these messages are distributions over 0, 1. Distributions over the assignments, or +1, -1. Okay, the messages are all probability distributions or assignments, and they're just stating the fact that MU to V is the marginal distribution of U in the absence of V, and so on. And you're pretending that the whole thing is a tree. If it was a tree, then you'd have at every point over here, at every node, you'd have the following thing. You have, let's say these are the edges here. At every node, every edge MU to V, for instance, the message out of U towards V is some function psi BP of the incoming messages on the remaining edges. M W to U, W in the neighborhood of U, but not equal to V. Okay. In a tree, intuitively we started with this idea that there's a root and this is like a special direction, and the message to the root is a function of the message you get from the children. But in a general graph, there is no direction associated. So you pretend the message on every edge, leaving on any edge, is a function of the messages incoming on the other edges. Okay. Is that it depends on the, well, it's not the same function, it depends on the degree.
But so it depends on the particular, yeah, I guess,
yeah,
in general, it will depend on the weights of things like that, or
right. Yeah, like let's say in stochastic block model, it depends on just on the degree, right? Because degree of U, but it's the same function in stochastic block model for on every edge of the same degree, every vertex of the same degree. Basically, as degree changes, the number of things you multiply changes. Yeah. But in general, yeah, if you did this with, let's say if you want to do this with something like a CSP, like a not all equal SAT, then the clean way to do it is to have two sets of nodes in your graph, the variables and the constraints, like the variable constraint graph, and do all of the cavity calculations over there. So when you remove a variable, the constraint will have an orphan, and when you constrain, the variables are an orphan. So there will be two different kinds of updates. The variable nodes have an update and constraint nodes have. Yeah. But so this is what, so this is a property that we hypothesize to be true for the distribution that we care about. That, locally at every node, there are these numbers MUV that characterize the distribution, and these numbers satisfy some relation like this. So it's like a fixed point relation. Okay, so you have some thing and you want to find a fixed point of this relation. So, okay, let's take a leap of faith and try to do the natural thing. You start at one point and you keep applying the same update rule again and again and hope that you converge to the fixed point. Okay, so that is a BP algorithm here. So what we do, you have messages on every edge in both directions on a graph, and you initialize these messages to some value. We'll come to that later. And then after you initialize it to some value, you just keep running the BP update rule again.
What's this? Oh, sorry.
Sorry? Questions on this?
It works on trees.
Yes, on trees you can prove that it's exact, and it's not hard. It's like we did almost all of the proof, except that if we do this, we are updating all the messages at the same time. So it will, but you can prove that it works on trees. It's not that hard. Okay, so this is the BP algorithm. Okay, so, and we don't know how many steps you want to run and so on. Okay, so let's think about this algorithm a little bit. What are the cons and the pros? Well, let's start with the cons. The con that I find very surprising, like a little bit difficult for me typically is that nothing about BP is obviously correct. There's no obvious, there are very few obvious facts that you can prove to be true about BP. So in particular, firstly, okay, BP is running this fixed point iteration to arrive at a fixed point. It's difficult to prove that you actually converge to a fixed point. Okay, so let's ignore that issue. Let's say I ran an exponential time algorithm to find the fixed point. Okay, we don't know if there's one fixed point or any number of fixed points. And even if you found a fixed point, even if there's a unique fixed point in your relation and you found it, we still don't know that that fixed point corresponds to the distribution that you care about. Because for it to correspond,
that's true, right?
Under the cavity hypothesis, well, even that you can't really prove. But it's not like I can write down a one-line cavity assumption under which the BP fixed point is the true distribution.
I mean, the cavity hypothesis is that the true marginals are a fixed point of the BP.
Yeah, you could say that. Yeah, you could say that. But even out there, it's a bit subtle because if you take the cavity assumption to be formally true, like if you say it has to be actually true, then we're in trouble because things are never going to be actually fully independent.
It's not equality, right?
Things will never be fully independent. Right? They'll be approximately independent, and you have to make an approximate cavity assumption, and then so nothing about it is obviously true. So it's like usually in algorithms, you do things that are obviously correct, and then you hope that something works. But here, nothing is obviously true. As I said, it's difficult to analyze because I guess I didn't write down the update rule. I have a cheat sheet. I have to do it at some point. I'll write down the update rule for SBM, but it's quite a nonlinear update rule. And another thing is, of course, it's difficult to talk about robustness of BP because it's a discrete dynamical system. It's hard to know where it goes, right? If you mess up some things, so it's quite a difficult thing to do. But what are the pros? Firstly, it's very efficient. Like it's a near linear time in some sense, right? And
assuming the number of iterations is small.
Right, yeah. Yeah, it works well in experiments, right? I mean, this is not just experiments. I mean, it's also used heavily, right? So it's like a very useful algorithm, right? Unlike SOS, I guess, for now. And then even from a theoretical standpoint, the reason it's very interesting is that, I mean, all the things that we said are not obviously true, are many times true for deeper reasons, and the whole fun is in proving that they're true, right? And in particular, for many cases, it is true. These facts are true, and in a sense, BP does characterize the optimal mean square error in many situations. So let me show why that sort of is the case.
Is there an optimized interpretation?
Right. So BP fixed points are local minima of a function called the Bethe free energy. So when BP arrives at a fixed point, or if you look at any BP fixed point, it's a local minimum of a Bethe free energy. But Bethe free energy is not a convex function, and this is not a gradient. Like this is not gradient descent on that space either. So,
Local minima correspond to
BP fixed points, yes. There's a correspondence as well, and between it's really syntactically corresponds to.
Are they local minima or critical points? Are they local minima or just? I think they're just first order critical points, right? Like they don't.
Oh yes. Oh, sorry. Yes. So they're just first order 2 points. Yeah, they're not really local minima. Yeah, that's right. Yeah. Okay, so why is even from a theoretical standpoint that we did all this? Why is it very interesting? Well, why is BP interesting? Because let's say you're interested in what is the optimal recovery rate you can get for, let's say, stochastic block model. Okay, so let's fix a vertex u. And how do you write down the optimal recovery? Let's fix a vertex u, fix its label to +1. Now sample the entire stochastic block model, the rest of the graph. Okay, okay, and then you ask, under the posterior distribution, P of x comma g, x given g, what is the probability that xu is 1? Okay, so what does this tell us? Well, if I started with the label u being 1, and then the rest of the vertices took some value +1, -1, and then you sample the graph and get conditioned on the graph, you get back a sample from for your planting. What is the chance that you get back +1? Right, and that really is in some sense, the optimal recovery rate you can hope here. You can't hope to get any recovery rate better than that. Okay. Right. Okay, so that's good. So this is like, if you want to understand this number, like this is a number in 0 and 1, right? And it tells you, in some sense, how well you can recover the original planted partition. If you, okay, and above the Kestenstiegem threshold, we expect this to be, or in fact, above the statistical threshold, we expect this to be some non-trivial number, and below it should be 0, tending to 0. Okay, so how does like, suppose you think about characterizing this number, proving the value of this number is something. So let's say you took this leap and you say, okay, for whenever you do this experiment, okay, you will get some probability for xu equal to +1. Okay, some probability for x equal to +1. Let d be the distribution of values of this. Okay, so d is a distribution over 0, 1. It's a distribution over 0, 1, which is whenever you do this experiment, what is the probability that xu equal to +1 in the, so each time you do this experiment, you get a probability and some distribution d. Okay, and so now let's pretend that this distribution is actually a real thing. It doesn't depend on n. It doesn't depend on this. It actually exists. Okay, let's pretend that d exists. It's not clear that d exists, right? Meaning maybe it's a mixture of two distributions and things like that. So, let's say d exists. For every n, it's the same distribution, and some distribution exists. Okay, and then let's also pretend the following is true: that if you look at any particular graph from in an SBM, okay, look at different vertices. The vertices have, and look at the distribution of these marginal values, that is also d, right? One is averaging over graphs, it's some d, and the other is in a given graph. Also, let's pretend that it's d, there's a distribution d, okay? Okay, so then what happens now? Well, here's a relation that d satisfies. Okay, so in G minus, we talked about how to sample the neighborhood of a vertex U. How do you sample the neighborhood of vertex U? We take U and we sample a Poisson number of minus neighbors, and we sample a Poisson number of plus neighbors. Okay, you sample some Poisson number of minus neighbors and plus neighbors, and you ask all the neighbors what their marginal values are. Their marginal values are, by assumption, samples from D. They're all samples from D. Well, D plus and D minus, but D and 1 minus D. But they're all samples given by this distribution D, right? Okay. So in some sense, like, and the output of your vertex is also a sample from D. Right? Just because of your assumption that
you can make some cavity assumption that they are independent.
Yeah. Under the cavity assumption, assume that the cavity assumption, and so D becomes a fixed point of the following relation, right? D is a fixed point of the following distributional relation. What is it? You sample two numbers, R and S, which is a number of vertices, plus vertices, and number of minus neighbors. Okay, and you take R samples from D, and 1 minus, sorry, S samples from 1 minus D. Okay, you take samples alpha, these are the samples, and then you plug them into this BP update rule, which takes in numbers and gives out a number. So it spits out a number gamma. Okay, so you have this constant sized, I mean, effectively constant sized operation, right? Because R and S are constants, D in and D out are constants. So it's really, there's no N in this. It's the key point is N is out of the picture. We have a fixed point relation on a constant size fixed point relation on distributions over 0, 1. So if D was this distribution over 0, 1, we tend to think that it satisfies this fixed point relation, meaning you do this operation, the number you output is also from D. That gamma is also from D. Okay, and that's the beauty of this. So now, we had no handle on D, like, we had to do this N, this thing on N vertex graphs, and, it was super hard. But now suddenly we have a surprisingly strong handle on D, the distribution of these marginal values, right? It's surprisingly, all of a sudden, it's the solution to a fixed point relation of constant size. If you write it out, it's some algebraic, if you write it out, it's some constant size algebraic set of equations, and D is a solution to that, in a sense. Okay, but it's a distributional fixed point. It's a fixed point relation for D. Yeah. Okay, is it clear? Any questions on this? So that's the reason why BP is interesting. So in the sense that when you try to characterize these things like what is the optimal recovery rate, or what is the mutual information or mean squared error and so on, you naturally, the cavity hypothesis starts giving you answers. And of course, the whole difficulty is in proving that the assumptions you made on the way are true. Okay, that's the technical difficulty, but at least this tells you where to go. And I think again and again, this sort of thing has been formalized rigorously in many, many settings. There's a whole line of work by Will Perkins and Kojau-Glan, and also Abe Montanari, and lots of works on these things. In lots of settings, you prove that the BP fixed point gives you the right answer.
So usually here, it will actually be the case that there will be a unique fixed point, and that will give you the right distribution, or?
No, I think it's very difficult to prove things. I mean, it needed a lot of work to prove things about the fixed point structures.
What would be the two? Like, would it usually be?
Oh, there could be a lot of spurious other fixed points, and also
even in this constant size.
Even in this constant size, there's a lot of. I think, for example, maybe somebody will correct me if I'm wrong. Even for community detection, only the dissociative case has been solved, and the associative case is still not solved, or the other way around. Like you need to make additional, like now the question, like at least one of the technical questions is to, as Boaz was saying, to understand the solution space of fixed points of this distributional relation, for example.
That's like the case where basically statistical physicists would look at that and they would say, okay, some of these solutions are non-physical, and then the one that's physical will kind of give them the answer. Yeah,
usually I think it's the, basically you look at the Bethe free energy, and the one that maximizes that is sort of the entropy, the free energy of the entropy, but basically the one that maximizes that is the one.
The BP can be written for, this is not a story of stochastic block model, right?
Right, yeah.
It can be written for the random constraint satisfaction problem.
Yes.
And sometimes the cavity equation is validated and BP works, but there is a regime where BP either probably doesn't work or strongly conjectural.
Yes.
In the condensation threshold above the. So
right. Yes. Yeah. No, I mean, so BP, right? So this doesn't always characterize. I mean, even like, if, for example, if you take 3-sat about the symmetry breaking, once the replica symmetry breaking happens, like these cavity assumptions won't be true, and then, but you have to do survey propagation or something. But this, I just want to give a flavor of why these things are very. why this thing is very useful somehow, the cavity assumption. It lets you start attacking these questions. Yeah. Okay, so, all right, so now let's go back to the algorithm. So now, okay, let's look at BP again. So the one thing we left out was, what is the initialization? How do I initialize these messages? Okay, there's usually in all of the Bayesian CSPs that I described, there is a notion of a naive initialization, which for stochastic block model corresponds to saying every marginal is with half probability +1 and half probability -1. Okay, this is the natural initialization. Okay, let's see what happens when you do this. Well, three things can happen. Firstly, you start with this naive initialization and you get stuck there, or you don't get stuck there, meaning BP in one iteration does something, it goes somewhere else. Okay, okay. This means that your original point is not a fixed point. It's a good case, like you don't get stuck in your first step. So that's good. So, and in fact, you can prove that you can get non-trivial recovery here. Actually, I must have said, I shouldn't say BP yields non-trivial recovery. I don't know how to prove it, but it's easy to get non-trivial recovery in these cases because there's some degree balance that's failing. It's, for example, if you sample planted 3-sat in the naive distribution, by looking at the variable, whether it's negated or not, you can figure out whether the variable should be 0 or 1, right? And so this is an easy case. Okay, but now let's say this naive initialization is a fixed point, meaning the BP doesn't move from there. You start with that, you stay there. Okay, in fact, for stochastic block model, this is a fixed point, right? Because if all the neighbors say that they are uniformly randomly ±1, by symmetry, the vertex will also be uniformly randomly ±1, just by symmetry. So there's this issue that if M is a fixed point, but then you're sort of stuck. But even if in this case, there are two things that can happen. One is your fixed point is somehow unstable. Okay, this all halves was bad. Let's say I perturb it a little bit. Do I move away? If all halves or is this naive fixed point is unstable, then the prediction is that there is an efficient recovery is possible. And if the fixed point is stable, then you cannot have, the prediction is that no efficient algorithm can get non-trivial recovery. Okay.
There is a fixed point that is stable and no efficient algorithm.
No, so for this particular initialization, in fact, it's you can think of the initialization as you had a prior, right? You just substitute the prior as your initialization. Okay, and right, yeah. No, I mean right. No, that's the claim. Yeah, that is the claim. Right. No, I mean prediction is really a prediction, right? It's yeah. I mean that's the nice thing. So it's really very simple to describe. So it is saying that if you take this naive initialization, substitute it, and if the fixed point is unstable, then you have an algorithm. You should have an algorithm. If it's stable, you shouldn't have an algorithm. Okay. So I've been saying stable, but really what I meant was stable on an infinite tree. Unstable on an infinite tree. Okay, so let me say what that is. So how much time do we have?
13 minutes.
Okay. Yeah. Okay, so let's see how much I can calculate and things. But okay, so what is stability on infinite tree? Well, okay, as we said, our neighborhoods look like trees, right? There's the infinite tree. And let's say you go up to some distance L, okay? And what we know is that we are at a fixed point, right? So if every node says, I'm uniformly randomly half, okay, then its parents also say half, and everybody says half. So it's like a fixed point, okay? Everything it's a fixed point. And so then what does stability mean? If I take the nodes at the children at depth L, and I perturb their values by epsilon, plus or minus epsilon. I perturb the values of the leaves by plus or minus epsilon. And then I ask, does the root change? The value at the root change? In particular, let's say epsilon is some fixed number. So for every epsilon, for sufficiently large depth, L, okay, you want that the marginal output of the root has some variance. It starts, right? Its variance of is strictly greater than 0. Then we would say this is unstable.
You want that like there is an absolute number that say
For the 0.
the zero.
Yeah. Let's say
Maybe stable means that for every epsilon there is a delta such that if L is sufficiently large, then the variance is less than delta.
yeah, right. Yes. Yeah. That's the right order of quantifiers. So you say for every epsilon, if I perturb by epsilon, if I go sufficiently large depth, I should be able to make the output perturbation smaller than delta for any delta. That's stable. But if I see the perturbation in the root, that's unstable.
What do you think variance?
Variance, because I defined it so that it's a random perturbation at the leaves. I made a random perturbation at the leaves. Right. Yeah, so the perturbation was random at the leaves. You're asking what happens at the root. Okay, so that's what stability of an infinite tree is. So it's so again, the key point here is there is, by saying something about an infinite tree, there is no n here. So right, that's sort of the key point here. In that this is a prediction which, like you make, this is a property of the model as opposed to any given n, because of its infinite property of the tree. And so, and the claim is that when the model satisfies stable, when a model has stable fixed points, the naive fixed point is stable, then it's no efficient algorithm. When the naive fixed point is unstable, there is an efficient algorithm. Okay. Yeah, a question there.
There quite a connection between those three cases and the solution space geometry.
Yeah, I don't know, maybe someone else might know this better. Yeah, I don't know if there's a connection known between stability of fixed points and solution space geometry. Yeah.
Like, what sort of perturbations are allowed? Like, could I have colluding perturbation across
These are random plus minus perturbations.
independent?
Independent random plus minus perturbations. Yeah. Actually, I was hoping to do this calculation and prove that this is actually shows that the value of the Keston-Stigm threshold, d epsilon squared, is greater than 1. The problem is easy, and d epsilon squared less than 1, less than is hard. You can derive the Keston-Stigm threshold from here, but I guess I'll run out of time if I try to write it. But because I want to cover other things. But the key point is that this is a property of the model, and it's also quite easy to check whether something is stable on the infinite tree. I mean, it needs a little bit of work, but you can basically construct like a finite size matrix whose spectral properties tell you whether it's stable or not. So we can write a computer program to check if it's stable or not according to this definition. Okay. Okay, so that's the stability in the tree, and this is a very bold conjecture right now. Okay, and what?
The positive side of the prediction here, it says efficient is possible with BP or
Not with BP. Well, it should, like the positive perturbations, it should be possible, but like in community detection, all of the work by Bordenau, Lillard, Masood, and work prior to that proved it for community detection. And in recent work with Mohanty and Liu, we show that this is positive side is true for all Bayesian CSPs, like all of the models. It's a generalization of this BLM non-backtracking walk, what happened to community models, but it's just the positive side is true. So in all the blue regions, there is an efficient algorithm to get non-trivial recovery.
So that prediction has been confirmed.
It's confirmed. It is confirmed.
But is that with BP or?
Not with BP. It's a spectral algorithm.
And BP is known not to work.
BP, yeah, we don't know how to analyze
I
it.
just don't know how to analyze. Okay.
Yeah, we
But
don't know how
it's,
to analyze
but is the prediction that even BP works, or it's not clear?
I guess
I mean, there's simulations where.
yeah, I don't know. Yeah, I don't know what the belief is, whether BP should work everywhere, but yeah.
Probably want an algorithm that has long-range correlation with output.
Mhm.
So a naive version of belief propagation will.
Right. Yeah. Actually, so I mean, so I'll actually come to this issue of algorithms tomorrow. I'll want to talk about this local and global algorithms. But the point is somehow that BP, it's easier to analyze if you are somewhat correlated with the true solution, so some constant amount of correlation with the true solution. If we start at a random point, we don't know how to analyze BP because it's a nonlinear update rule, fairly nonlinear update rule. Basically, we can analyze BP for constant number of rounds. Even that is very difficult. It's very difficult to analyze BP for log n rounds. And to solve these problems, you need to have something like a power iteration, which does log n round, like a log n round thing. Yeah, and I don't know what the belief is whether BP should work in general, because in some sense I don't think statistical physics intuitions tell us anything about that BP should work here, because BP, I mean, up to the point where we did cavity method, it was all statistical physics, and the point at which said, okay, we want to find a fixed point, let's just iterate, we went away from physics. I think we are in our own now. So
outside of stochastic block model, belief propagation probably fails. For random constraint refraction problem, it probably fails regardless of the number of iterations.
right.
So I guess it's open for the within the domain of stochastic block models. Whether this,
Yeah, actually, you probably know better than this. Yeah.
no, but not so much for stochastic block models. So the conjecture is that it's within the for stochastic block models that this conjecture is true or even beyond.
Oh, this prediction. I mean, so okay. So I should say I'm associating this conjecture with it's not that there's precisely state this conjecture for a given problem in any of the papers. It's sort of this intuition which they give out in the text, where apply to different problems, and in each of the cases, the claim is that when it is not a fixed point, it's unstable. When it's an unstable fixed point, there should be an algorithm, it should be easy. And then, I should maybe not, maybe this is like a bit of my interpretation of the papers in a sense, yeah. But
so the intuition why the naive initialization makes sense to look at is that basically, if it's not a fixed point, you would expect at least that you can at least do some non-trivial recovery in the sense that you get something that's correlated with the solution. Maybe you don't get exactly the solution, but you get something that's correlated with it.
right. Yeah. I mean, the naive initialization in Bayesian CSP is very natural. It's just the prior you started. It's like the prior on the variables. So yeah. Okay, so that's good. All right. So okay, so in fact, this is how we drew all the pictures that I showed earlier. You do this calculation on the infinite tree. You can write a program to do that, and you say when it's stable, when it's unstable, you can draw those pictures. It's a good exercise. Right. Okay. So now let's see how we can take this BP intuition to get an actual algorithm, provable algorithm. And the idea is also very much there already. So what is the idea? Well, let's just analyze stability of BP, of the BP update rule in a general graph. Okay, so what is it? So you have a fixed point here. So you have a fixed point. Okay, let's say the naive fixed point is a naive fixed point. And then you want to know whether the fixed point is stable. Well, the fixed point is stable with, if you just do Taylor series expansion or take a linear approximation, you can write down the difference when you perturb the input by a little bit, by epsilon. The output perturbation is given by the Jacobian of the BP update rule. So note that psi is a map from R to the 2 times E to R. It's a multivariate function that takes 2 times E variables and gives out 2 times E variables, right? It's a map. And you can write down its Jacobian, which is the matrix of partial derivatives. You can write down the matrix of partial derivatives. And then standard calculus thing, the fixed point is stable in a sense if and only if the spectral norm of this matrix is less than 1. Okay, so I mean, what key point is that now I'm talking about stability in a general graph, and so but we're sort of trying to use the same intuition and say, okay, let's just look at the fixed point.
So I'm just since you talked about random epsilon, should it be some kind of Frobenius norm, or should it be a spectral norm, or how does it?
Yeah. Okay. So so it is a spectral norm, and I mean okay. So the reason we looked at random perturbation in the tree and the worst case perturbation in a general graph is that if you look at the spectral norm of J of psi for a general graph, J of psi, the spectral norm is controlled by the random perturbation quantity in a tree. Essentially, if you want to say, the idea is that in some sense, every neighborhood every vertex has its own tree, right? And so whatever assignment you put, whatever perturbation you put, for most of the vertices, the perturbation looks random from their point of view, right? But basically, I mean, there's no, I mean, that's the intuition which I'm giving, but there's a formal theorem you can prove that okay, let's look at this matrix. This matrix is now, it's a matrix of partial derivatives. Okay, it's an important matrix to know. So let me just say how big it is. It's 2 times edges. For every edge, there are 2 rows and 2 columns for it, for every edge. Okay, and the non-zero entries of this matrix are only on entries of the form ij to jk. So if I have ij, edge ij, and then edge jk, in the column ij, I to j, and the row j to k, or row I to j and column j to k, there's a non-zero entry, which is given by the partial derivative of the BP update rule for this vertex. Okay, I actually planned to write this down, but I guess we're running out of time. But you can essentially, write down the entries of the matrix one by one, because it's really the list of partial derivatives of a polynomial relation or a nonlinear update rule that you wrote down. Okay, evaluated at a point. So that's the matrix, and the claim is if that matrix has spectral norm less than 1, then the fixed point is stable. If it's more than 1, the fixed point is unstable. Okay, and this matrix, the spectral norm of this matrix is the distinguisher between the planted and random that we can use to get an algorithm. So in particular, in stochastic block model, which is our original problem, these partial derivatives are all some fixed constants. It's a particular fixed constant, e to the minus beta. Okay, it's a fixed constant. Actually, it's not. Okay, so what that means is that this matrix of partial derivatives is it's e to the minus beta times a 1 on the entry I to j, j to k. You put a 1 whenever for every edge ij and jk, put a 1. Okay, that's the matrix, and that's a non-backtracking walk matrix. Okay, and the spectral norm of this non-backtracking walk matrix controls the it's just a spectrum of this non-backtracking walk matrix. It turns out is a distinguisher between planted and random, and that's the part which requires a proof. What do we need to prove? We need to prove that when this condition on infinite tree, the stability condition on the infinite tree holds, then the spectral norm of this random matrix is bounded. And when it is unstable, you have a large eigenvalue. Okay, so you have to translate this stability condition on a tree to the spectral norm of random matrices that you draw from it. For example, for stochastic block model, it's just like you take an Euler-Shriny graph and construct this non-backtracking walk matrix. You need to prove that the eigenvalue, the largest eigenvalue, after you take out the trivial eigenvalue, is at most square root d in a Euler-Shriny graph, and that's what BLM did. We do it for a more general model of not all equal CSPs. I say not all, just Bayesian CSPs. For Bayesian CSPs, it's true that the random matrices that you get have spectral norms that can work as distinguishers between planetary and random. Yeah, sorry, yeah, it was a bit messed up. Any questions on this?
Because from the fact that you want to look at the stability, you can need to provide a partial derivative exists. Why the I to j, j to k sort of matrix with like two edges?
Well, that's because of the following simple reason that in general, right, if I look at the partial derivative of the I to j in terms of k to L, this is 0 unless L is equal to I, because for every vertex, the output message is just a function of these input messages, right? So this is the output message I to j. It's just a function of edges that enter here. It's independent, like when you differentiate partial derivative, it will be 0 if you try to take a partial derivative with respect to some other edge somewhere. That's why you get this non-backtracking structure naturally. Yeah. Any other questions? Yeah. Okay, so that I talked about the detection. The recovery is a little bit more subtle than what you expect, because the eigenvector, remember that this matrix is not a symmetric matrix. So its eigenvalues are actually complex. So it doesn't naturally correspond to an optimization problem, in the sense that you can't take the eigenvector of this matrix and think of it as the solution to some optimization problem, as in it doesn't correspond to max cut or min cut in the usual way spectral eigenvectors of Laplacians do. So recovery is more subtle than what you usually expect from spectral algorithm. Just take the eigenvector and do something with it. Okay, I think I'll stop here. Tomorrow I'll talk about sum of squares. Please.
Any more questions? All right. Wow.